Hello again, Nicole Mashburn, and today we're going to continue our discussion of chemistry, and we're going to focus on inorganic chemistry. Now, this is going to be what you need to know for this course. There are inorganic chemistry classes that last entire semesters and even entire years. This is just going to be the inorganic chemistry that's relevant for our course. So when we think about chemistry, we can divide chemistry into two main classes of compounds. We have inorganic compounds and organic compounds. And when we think about inorganic compounds, we're talking about things like water, salts, acids, and bases. These are all things that do not contain carbon. Now, I never say never because there's always an exception. And so the exceptions are carbon monoxide and carbon dioxide. Okay, so carbon dioxide, that's what we breathe out as we're respiring and breathing. Bring oxygen in, blow out CO2. Carbon monoxide is the gas that's produced when something's burning. So if you have a gas fireplace and you have a carbon monoxide detector, it can be toxic. So except for carbon dioxide and carbon monoxide, your inorganic compounds would include water, salts, acids, and bases. And this is what we're going to focus on today. Your organic compounds, and I'm going to do this in a separate lecture, are the things that have carbon, okay? And these are usually large molecules or large compounds. And so, for example, you have carbohydrates, which are your sugars. You have fats, proteins, and nucleic acids, and that's like DNA. That's an example of a nucleic acid. So we're going to focus on the organic compounds in a later conversation. So today we're going to focus on these inorganics, water, salts, acids, and bases. So the first inorganic compound would be water. And water is the most important inorganic compound in living organisms. Most of your body weight is water. 60 to 80% of the volume in your cells is actually water. Water has some very unique properties that make it well suited for living organisms. And one of those is that it absorbs and releases heat slowly. So let me give you a non-living example before I give you a living example. So imagine you took a pot of water and put it on the stove. Turn on the heat. Does it boil immediately? No. It takes a while for that heat to be absorbed and the temperature to go up and the water to boil. Now let's remove the water from the heat. Does it immediately go back to room temperature? No, it takes a while for that heat to be released and the water to cool down. Well, the same thing happens in our body. So the fact that we're mostly water prevents sudden changes in our temperature. So if your body temperature is 98.6, if you walk outside and the temperature is 110, you're not immediately going to have your body temperature raised to 110. It'll take a while for the water in your body to absorb all that heat. And so we have some mechanisms to prevent that. I'll talk about that in just a second. But you won't immediately become 110 degrees. Hopefully you'll never become 110 degrees. If you walk outside and the temperature is 0, you won't immediately freeze, okay? All your heat will not dissipate and you won't turn into an ice cube immediately. Over time you might if you're out of homeostasis, but again, the fact that water absorbs and releases heat slowly prevents you from immediately boiling or immediately freezing when you walk outside. Now, this water also has a nice property. It allows you to cool through evaporation. So if you do walk outside and it's hot, you begin to sweat. And that's water being released. It evaporates, and as it evaporates, it takes the heat with it. So we use water to help us stay cool. Water is also a universal solvent. That means things dissolve in it. So our chemical reactions can take place in water. It's also the major transport mechanism. So we use blood to transport things throughout our body, nutrients, gases like oxygen and carbon dioxide, blood cells. And so plasma, the liquid part of blood, is mostly water. So we use it for transport. We also use it to cushion our vital organs. So most of our organs are sitting in kind of a fluid-filled sac. You may have heard about the pericardial membranes, and your heart's kind of sitting in a fluid-filled sac. That serous fluid that surrounds the heart is mostly water. So it allows some cushioning for your organs. And it also plays a role in electrolyte balance. And electrolytes are ions. So these are things like sodium, potassium, chloride. And these are things that our bodies use for our nervous system. It allows us to maintain the amount of water in our body. We're going to talk about fluid and electrolyte balance a little bit later on, but water's an important role, plays an important role in maintaining that fluid and electrolyte balance. Okay, so the next inorganic compound are your salts. And these are ionic compounds that dissociate in water. So these are things that break apart in water. So for example, sodium chloride. Okay, so if you have a salt, table salt, sodium chloride, and you put it in water, it will break up into sodium and chloride, which are ions, which are your electrolytes. So these are going to be cations, which are the positive ions that are not hydrogen. So anything that's positive that's not a hydrogen. And anions are things that are negative, so anything that's negative other than an OH. This is called hydroxyl. So your salts are any compounds that break apart in water that are either positive, but not hydrogen, or negative, but not hydroxyl. And so some examples of that would be sodium chloride, potassium chloride, this is calcium carbonate, this is calcium phosphate. These are important in your bones. And so these ions are electrolytes. Because they have charge, they help us to conduct electrical currents. So our nervous system, say NS for nervous system, it basically works by allowing charges to flow through the nerves. And those charges that flow are going to be sodium and potassium. And we'll talk about that later on as well. So we use these electrolytes in nerve conduction. These salts, think about bone, and remember salts are usually crystals. And so think about bones and teeth are kind of glorified crystals. So bone and teeth are hard because of the salts that are in calcium carbonate and calcium phosphate give your bone and teeth their hardness. And again, they play a role in electrolyte balance. I'm going to go ahead and give you one little clue. Wherever you find sodium, you find water. Water always follows sodium. So wherever there's a high amount of sodium in your body, water is going to be kind of drawn to that. And so if you need to maintain water in your body, you'll basically hold on to sodium, and that'll hold on to the water. So again, we're going to talk more about fluid electrolyte balance in this semester, and then we'll cover it even more in your second semester of anatomy and physiology. All right, so the last class of inorganic compounds are your acids and your bases. Okay, acids and bases. And again, these are both electrolytes, okay? But they are not salts. These are things that have a hydrogen. Acids have a hydrogen, and bases have that hydroxyl group, okay? And so these are things that break apart in water and either are containing an H or an OH, okay? So acids are proton donors. That means when an acid breaks apart in water, it's going to release that hydrogen ion into the water. So this would be hydrochloric acid, and when it dissociates, you get a hydrogen atom and a chlorine ion. And so acid solutions will contain lots of these hydrogens, and we call these hydrogens protons. That's just another way of talking about hydrogens. The more hydrogens you have in a solution, the more acidic it becomes. Okay, so the more hydrogen, the more acid it is. Hydrochloric acid is one of our important acids in our body. We find it in our intestinal tract and our stomach to help us break down foods. So I do want you to recognize HCl as hydrochloric acid. There's many, many, many acids, but this is the one I want you to know right now. Your bases are proton acceptors. That means they take up hydrogen from solution. So this one is sodium hydroxide, and so when sodium hydroxide breaks apart, it becomes sodium and hydroxyl ion. And this hydroxyl ion, because it's negative, it will accept that proton from hydrogen. So because negative and positive are going to attract each other. So one hydroxyl ion and one hydrogen ion will make water, okay? And so when you talk about bases, you also use the word alkaline. So a basic solution is also an alkaline solution. And alkaline solutions are going to have a lot of these OHs. So you're going to have fewer and fewer protons. So the more basic something becomes, so the fewer the protons you have, the more OHs you have, and the more basic or alkaline it becomes. So alkalinity and basic mean the same thing. Some Other examples of some bases besides sodium hydroxide are your bicarbonate ion and ammonia, and these are some important bases that we use in our body as well. So when we talk about acids and bases, we have to talk about pH. So what is pH? pH is basically the concentration of hydrogen in solution. So it's a measure of how many hydrogen ions are in solution. Okay, that's what pH means. How many hydrogen ions do you have in your solution? So if you think about water, which is H2O, and remember I told you that's just an H and an OH put together. So one positive, one negative, it is neutral. Okay, it is a neutral liquid. And if you were measuring it on a pH scale, it has a pH of 7. Okay, so we're going to talk about the pH scale. So just remember, 7 is neutral, and that's water. So when we're talking about pH, we're talking about things that are acidic and alkaline. Remember, alkaline also means basic. So an acidic solution has the highest number of hydrogen ions. So the higher or the more hydrogen ions you have in concentration, the lower the pH. The lower the pH, the more acidic the solution. Okay? And so acidic pH is anything from 0 to 6.99. Now your pH scale is going to be 0 to 14, with 7 being neutral. So anything from 0 to 7 or 6.99 is an acid, and anything above 7 is going to be a base or alkaline. Now your pH scale is logarithmic. That means a pH of 5 has 10 times more hydrogen ions than a pH of 6. So pH 5 is more acidic than pH of 6. Your alkaline solutions, or your basic solutions, they have a lower number of hydrogen ions, and so the pH is higher. Okay, so it's going to be a higher number, 7.01 to 14. So the fewer hydrogen ions you have, the higher the pH, and that's going to be the higher the actual pH number. Okay, so the higher the pH, the more alkaline or more basic it becomes. So this is your pH scale, and over here you have a measure of how many hydrogens or how many hydroxyl ions are in solution. Okay, so here we have examples of things that are considered acids and bases. So here's neutral, and this will be water. Okay, now as you're going down the pH scale from basically lower than 7, from 0 to 7, these are all your acids. Okay, anything above 7, 7 to 14, these are your bases. So this is becoming acidic, going down to 0, and going up to 14 is becoming more alkaline or basic. So as you go down your scale from 7 to 0, you're becoming more and more acidic. That means you have more and more hydrogens. So the more acidic it is, the more hydrogens you have. So the lower the pH scale number, the higher the acidity. Okay, that means you have the most hydrogen ions in solution. If you look at the basic side, the higher you go on the pH scale, okay, as the numbers go up from 7 to 14, then you have fewer and fewer hydrogen ions and more hydroxyl ions. Okay, does it make sense? It's a little, let's think about this. It seems like a little backwards. So remember, the more hydrogen ions, the more acidic it is, but the lower the number means it's a higher acidity. I know that's kind of confusing. You have to think about it for just a little bit. All right, so some examples. Blood is 7.4, so it's a little bit basic. Milk has a pH of around 6.3, so it's a little acidic. Coffee is more acidic, it's a pH of 5. Wine is even more acidic. Remember, the lower the number, the higher the acidity level. So your highest acidic level on this scale is hydrochloric acid. This is very, very acidic. Going the other way, egg whites are considered basic. They have a pH of 8. Go more basic, pH of 9.5 would be household bleach. Ammonia has a pH of about 10 to 11. Sodium hydroxide would be your most basic with a pH of 14. So take a little while to study this and get some examples of different pHs and understand the more acidic it is, the lower the number. The more basic it is, the higher the number. Okay? Now, why do we care? Well, here's that word again, homeostasis. We are trying to maintain homeostasis. And so there's many things that we have to maintain. We have to maintain our temperature. We have to maintain our blood sugar levels. We have to maintain the oxygen in our blood, the carbon dioxide in our blood. All of these things have to be maintained. And another thing that has to be maintained is our pH. Okay, pH is very important. Cells function best at a very tightly regulated pH. If pH changes outside of this tightly regulated pH, you can actually cause tissue damage. So any just very small changes in pH can actually kill you. And the things that control your pH, and we're going to cover this really in detail in your second semester of A&P, but the things that mostly regulate your pH are going to be your kidneys and your lungs, and then there's a buffer system in your blood. And we'll talk about each one of these. So your normal blood pH should stay in this range of 7.35 to 7.45. Now, I rarely ask you to just memorize a number, but I do want you to know this. Okay, so blood pH should be 7.35 to 7.45. That's the range that everything's okay. And that is slightly basic. So blood, again, is slightly basic. If your blood pH falls below 7.35, we say that condition is called acidosis. So if someone's acidotic, their blood pH has dropped below 7.35. If their blood pH has risen above 7.45, we say they're in alkalosis. Okay, and so if someone goes to the hospital, they take a blood draw, they check the pH, and it's below 7.35, they'll say you're in acidosis. It's above 7.45, they'll say you're in alkalosis. Again, we're going to cover this in a lot more detail in your second semester. Any change in pH can either be due to a respiratory change, either you're breathing too slow or breathing too fast, or a metabolic change. So possibly your kidneys aren't functioning very well, or they're over-functioning, or they're doing something that they're not supposed to be doing. Or maybe they're compensating. So maybe your lungs aren't doing what they're supposed to be doing and your kidneys are trying to help. Or maybe your kidneys aren't doing what they're supposed to be doing and your lungs are trying to help. Again, we're going to cover all of that later. Right now we're just going to do some basic acid-base homeostasis. So what are some examples of your respiratory system affecting your pH? So remember, respiratory is breathing, okay? Breathing in oxygen, blowing out CO2. And so if you breathe too fast, if you hyperventilate, the condition that's going to result is called respiratory alkalosis. So that's more what? Basic. So why does that happen? Well, CO2, carbon dioxide, which is the byproduct of your cells doing their thing. We're going to talk about cellular respiration later, but one of the things that the byproduct of cells living is they give off CO2. And so you've got to get rid of that CO2 in your body. It's kind of a toxic compound to your body. We don't like to have a lot of that in our bodies. Actually, if you hold your breath, what makes you want to breathe is not that you need oxygen, is that you're trying to blow off the CO2. The CO2 is building up in your system, and it makes you want to breathe so you can breathe that out. Well, to carry CO2 in our blood, because remember it's a gas, we actually convert it to something called carbonic acid, and that's how we transfer the carbon dioxide in our blood. And so if you're breathing quickly, hyperventilating, then you're breathing off a lot of CO2. So you don't have as much CO2 to make that carbonic acid, okay? So you don't have enough acid. So if you don't have enough acid, that means your blood's becoming more basic, okay? Your pH is going up, all right? If you're breathing slowly, which is called hypoventilation, and you're not breathing off CO2 fast enough, then that CO2 is accumulating in your blood and making more carbonic acid. So if you have more acid in your blood, then your blood pH is going to go down. It's going to become more acidic. So breathing too fast leads to respiratory alkalosis, and breathing too slow leads to respiratory acidosis. And again, this is because of the way we carry carbon dioxide in our blood as carbonic acid. And so this is really all you need to know right now about respiratory breathing and acid base, but we'll talk more in detail again in your next semester. Now, what about metabolic changes? Things that are happening that are other than breathing. So there's several different things that can happen that can change your blood pH. One of these is vomiting. So if you just have a kind of a quick stomach bug, it doesn't last for long, you just throw it 1 or 2 times, your stomach has an acid, hydrochloric acid, and if you get rid of that acid, so when you're throwing that up, it'll actually start to affect your blood pH. So if you get rid of that hydrochloric acid, then your blood pH is going to go up. You're going to become more alkalotic or more basic. And we call that metabolic alkalosis. Now, if you've been sick for days and you've got severe throwing up, where you've thrown up all your stomach contents and now you're actually starting to bring things out of your small intestine, your stomach has hydrochloric acid in it. And so as the food contents have been digested and they move from the stomach to the small intestine, we have to neutralize that acid. And so your stomach, as those contents leave your stomach and go into your small intestine has something called HCO3, which is a base. And that will neutralize that acid in your stomach. And so that way the acid won't eat into your small intestine. Well, if you're throwing up a lot and you're starting to pull things out of your small intestine, you're going to start getting rid of that base. And so if you're getting rid of that base, that causes your blood pH to go down or become more acidotic. So mild vomiting causes metabolic alkalosis. Severe vomiting causes metabolic acidosis. You can also have these occurring due to kidney damage. So if your kidneys are not working like they're supposed to, it will change the amount of hydrogen ions you're excreting. Okay, so you may not be getting rid of enough, or you may be getting rid of too many. If you're getting rid of too many, your blood will become alkalotic. If you're holding on to too much hydrogen, your blood will become acidotic. Okay, so again, we're going to cover these in more detail in your second unit, second course, but I just wanted to kind of introduce it to you now because it is an important reason that we need to even know about pH. All right, and the last thing we're going to talk about are your buffers. And buffers are things, they're compounds that resist changes in pH. So one buffer that most people are kind of familiar with is Tums. So if you have heartburn, you'll take a Tums. So heartburn is due to the acid in your stomach kind of refluxing up and getting into your esophagus and causing it to burn, and it kind of hurts. And so you take a Tums, which is a base, and so that base plus that acid basically neutralizes it. Okay, so you take a base to neutralize the acid. And what it does, the way it does that, it actually converts a strong acid or base into a weak one, so the weak ones aren't as caustic, they don't hurt as bad. So again, you could take a TUM to neutralize the acid in your body. Well, in our blood, we're always trying to maintain that 735 to 745, so we actually have a buffer in our blood that will keep those pHs from changing very drastically. So if we're normal, if our respirations are fine, and our metabolic systems are fine, there's no problems with our kidneys or our lungs, then this carbonic acid bicarbonate system is all we need. It's a buffer system. And so our blood has carbonic acid and bicarbonate in the blood, so you have an acid and a base in the blood. They are going to basically work against each other to neutralize each other and keep your blood pH stable. And again, we're going to talk about buffers when we get into our second semester as well. But we do have buffers in our body, in our blood, to help neutralize and maintain that real steady pH of 735 to 745, as long as everything else is going okay in our body, as long as we're not having respiratory or metabolic issues. Now, there is a place in your mastering, if you go to the study area, to interactive physiology, and there's a fluid and electrolyte acid-base balance overview. I would really encourage you to go to mastering and do this on your own as a good way to review, because these are some really key information concepts that you need to be able to have a good grasp on. So if you haven't had a chance, or if you've never had this kind of chemistry before, fluid and acid base balance and things like that, take some time to go to the self-study area and work through those activities, and you'll learn more about it. All right, that's all I'm going to talk about today. Thank you.